The story of a neighbor in the night sky. There's something humbling about having a neighbor you can see, but never visit. Andromeda sits in the autumn sky, a faint smudge of light that's been watched by humans for thousands of years. Ancient stargazers saw it and wondered what it was. A cloud? A tear in the fabric of the heavens? They had no way of knowing they were looking at an entire galaxy, a cosmic island containing more stars than they could count in 1,000 lifetimes. Andromeda has been there all along, silent and patient, waiting for us to understand what we were seeing. And now we do. We know it's a galaxy, much like our own, spinning slowly through space, filled with stars and worlds and mysteries. We know it's approaching us, that one day our galaxies will merge. But for now, it remains a neighbor, close enough to study, far enough to remain forever out of reach. A reminder that we're not alone in the universe, even if we're separated by distances too vast to cross. The glow you can see with your eyes. On a dark, moonless night, far from city lights, you can see Andromeda without any equipment, just your eyes. Look toward the constellation Andromeda in autumn, and you'll find it, a faint, fuzzy patch of light, barely noticeable at first. It doesn't look like much, not dramatic, like the moon, or bright like Venus. Just a subtle glow, easy to miss. But that glow is extraordinary. It's the combined light of 1,000,000,000,000 stars, compressed by distance into a single soft gleam. When you see it, you're looking back in time. The light that's entering your eyes left Andromeda over 2 million years ago, long before humans existed. You're seeing it not as it is now, but as it was in the deep past. And you're seeing it with the same eyes that ancient peoples used, the same biological instruments that watched the sky before telescopes, before science, before we knew what galaxies were. Andromeda's glow is a gift, a connection to the cosmos that requires nothing but darkness and patience. The closest spiral galaxy to Earth, Andromeda holds a title. It's the closest large spiral galaxy to Earth. There are smaller galaxies closer to us, dwarf galaxies orbiting the Milky Way, irregular blobs of stars scattered nearby. But as far as grand spirals go, galaxies with graceful arms and billions of stars, Andromeda is our nearest neighbor. It sits about 2.5 million light-years away, a distance so vast it defies intuition. If you could travel at the speed of light, it would still take you 2.5 million years to get there. And yet, in cosmic terms, Andromeda is practically next door. The universe is filled with galaxies, scattered across billions of light years, most of them so distant we can barely detect them. But Andromeda is here, in our local neighborhood, close enough to study in detail. We can resolve individual stars in its outer regions. We can map its structure, measure its motion, trace its history. Andromeda is close, and that proximity makes it one of the most important galaxies in astronomy. The vast beauty of Andromeda. Look at a detailed image of Andromeda, and you'll see beauty that's hard to put into words. The golden glow of its core, packed with ancient stars, the delicate spiral arms, traced in blue and pink, where young stars are being born, the dark lanes of dust, winding through the arms, like rivers through a landscape, the faint outer halo, stretching beyond the visible disk, filled with old stars and globular clusters. Andromeda is a masterpiece, not crafted by any artist, but shaped by gravity, time, and the endless motion of stars and gas. Every part of it tells a story. The bright core speaks of billions of years of stellar evolution. The spiral arms show us where new generations are forming. The dust lanes reveal the raw material for future stars. And all of it, every star, every cloud, every glowing nebula, is held together by gravity's invisible hand. Andromeda's beauty isn't just aesthetic. It's a window into the processes that shape galaxies, that turn gas and dust into stars, that transform chaos into structure. The ancient light reaching us tonight, The light you see from Andromeda tonight is ancient. It began its journey over 2 million years ago, when Earth was in the Pliocene epoch. Our ancestors hadn't yet evolved. The continents were in different positions. Megafauna roamed the plains, and in Andromeda, 1 trillion stars were shining, their light spreading outward in all directions. Some of that light, an infinitesimally small fraction, traveled across the void toward what would one day be Earth. It crossed the space between galaxies, threading through cosmic voids, passing distant stars, until finally, tonight, it arrived. It entered Earth's atmosphere, reached the ground, and either struck your eye or a telescope's mirror. That light is a messenger. It carries information about Andromeda, as it was in the distant past. The spectrum tells us what elements its stars contain. The brightness reveals its distance. The motion, measured through redshift and blueshift, shows us it's approaching. Ancient light, reaching us tonight, a connection across time and space. The discovery of a nebulous mystery. For centuries, Andromeda was just a curiosity. Astronomers saw it through their telescopes and cataloged it as a nebula, a fuzzy patch, different from stars, but not clearly understood. Was it a cloud of gas? A cluster of unresolved stars? Something else entirely? They didn't know. In 1764, Charles Messier included it in his catalog as MF31, the 31st entry in his list of objects that weren't comets. Messier was hunting for comets, and these fuzzy objects kept confusing him, so he cataloged them to avoid future confusion. He had no idea what MEF31 really was, just that it was there, glowing softly, refusing to reveal its secrets. For over a century, Andromeda remained a mystery, a nebulous object in the sky, defying explanation. Telescopes improved, observations became more detailed, but the fundamental question remained unanswered. The answer, when it finally came, would revolutionize our understanding of the universe. The astronomers who first saw it, long before Messier, people had seen Andromeda. The Persian astronomer Abd al-Rahman al-Sufi described it in 964 AD as a little cloud, visible to the naked eye. He was probably the first to record it in writing, though countless others must have noticed it over the millennia. Later, as telescopes improved, more astronomers observed it. William Herschel pointed his large reflector at it and noted its structure. Others sketched its shape, noting the bright core and the extended halo. Each observation added a piece to the puzzle, but none could explain what it was. These early astronomers were looking at an entire galaxy, but they had no framework for understanding that. The concept of galaxies beyond our own didn't exist yet, so they called it a nebula and moved on, unaware that they were glimpsing something far grander than they could imagine. The astronomers who first saw Andromeda were looking at infinity, and they didn't even know it. The mistaken identity of a spiral nebula. By the early 20th century, telescopes had improved enough to reveal Andromeda's structure. It wasn't just a fuzzy blob. It had shape, spiral arms, winding outward from a bright core. Astronomers called objects like it spiral nebulae, assuming they were clouds of gas and dust within our own galaxy, perhaps solar systems in formation. The idea that they could be entire galaxies, separate from the Milky Way, seemed absurd. How could something so far away be visible at all? Surely these spirals were local, nearby objects, just unusual formations within our cosmic neighborhood. This misconception persisted for years. Debates raged in the astronomical community. Were spiral nebulae part of the Milky Way, or were they island universes, separate galaxies, scattered through a much larger cosmos? It was one of the biggest questions in astronomy. Andromeda, the brightest spiral nebula in the sky, was at the center of the debate. The truth would soon emerge, and it would change everything. The debate over the island universes. In 1920, two astronomers faced off in what became known as the Great Debate. Harlow Shapley argued that spiral nebulae were part of the Milky Way, that our galaxy was essentially the entire universe. Heber Curtis argued the opposite, that spiral nebulae were separate galaxies, island universes scattered through a cosmos far larger than anyone had imagined. Neither had definitive proof, but the debate crystallized the question, and Andromeda was the key. If someone could measure its distance, they could settle the argument once and for all. The tools existed, thanks to a special type of star called a Cepheid variable. These stars pulse regularly, and their period of pulsation is linked to their intrinsic brightness. By measuring how bright they appear, you can calculate their distance. All someone needed to do was find Cepheids in Andromeda and measure them. Easier said than done. But in the early 1920s, one astronomer would do exactly that, the moment humanity realized its scale. In 1923, Edwin Hubble pointed the 100-inch Hooker telescope at Andromeda and found what he was looking for: Cepheid's variables, stars whose brightness changed in predictable patterns. He measured their periods, calculated their distances, and realized something astonishing. Andromeda wasn't nearby. It was unimaginably far away, nearly 1,000,000 light-years. By his initial estimate, later refined to over 2,000,000, that distance meant Andromeda couldn't possibly be part of the Milky Way. It was too far. It had to be a separate galaxy, an island universe. Hubble's discovery was a turning point in human history. Suddenly, the universe wasn't just the Milky Way. It was filled with galaxies, countless island universes, each containing billions of stars. We weren't just small, we were incomprehensibly small. And Andromeda, that faint fuzzy patch, was an entire galaxy, a neighbor in a cosmos far grander than we'd ever imagined. The universe had expanded, and humanity's place in it had shrunk. The great expansion of the known universe. Hubble's discovery didn't just add Andromeda to the cosmic map. It opened the floodgates. If Andromeda was a separate galaxy, then so were all the other spiral nebulae. The universe was filled with them. Millions, billions of galaxies, scattered across unimaginable distances, each one a collection of stars, gas, and dust, each one a cosmos unto itself. The known universe expanded overnight. What had been a single galaxy, the Milky Way, became a universe of galaxies. And with that expansion came new questions. How did galaxies form? How old were they? Were they moving? If so, how fast, and in what direction? The discovery of Andromeda's true nature launched modern cosmology, the study of the universe as a whole. And it all started with one astronomer, one telescope, and one faint fuzzy patch in the night sky. Andromeda was the key that unlocked the cosmos. The first photographs of Andromeda. Before Hubble's breakthrough, astronomers had been photographing Andromeda for decades. Early photographic plates captured its glow, revealing details invisible to the eye. The spiral structure became clearer. The bright core and the extended disk. The dark lanes of dust threading through the arms. These photographs were revolutionary. For the first time, astronomers could study Andromeda at their leisure, examining the plates for hours, measuring positions, tracking changes over time. Photography transformed astronomy from a fleeting visual experience to a permanent record, and Andromeda was one of the first deep sky objects to benefit. The images revealed complexity that sketches had missed, structures within structures, layers of detail. Every new photograph showed something new, pushing the boundaries of what we knew. Those early plates are still valuable today. Historical records of Andromeda's appearance over a century ago. They're snapshots of a galaxy frozen in time, windows into the past. The telescope that revealed its shape, the 100-inch Hooker telescope on Mount Wilson, was the instrument that changed everything. Built in 1917, it was the largest telescope in the world at the time, a giant reflector capable of gathering light like nothing before it. When Hubble turned it toward Andromeda, he could resolve individual stars in its outer regions. He could study its structure in unprecedented detail. The telescope revealed the spiral arms, the bright core, the clusters of stars scattered throughout. It showed Andromeda not as a fuzzy blob, but as a structured, organized system, a galaxy. The Hooker telescope was a window into the universe, and through it, humanity glimpsed infinity. Other telescopes would follow, larger and more powerful, but the Hooker was the first to show us the truth about Andromeda. It was the instrument that expanded the cosmos, that revealed the universe's true scale, a monument to human curiosity and ingenuity. The spiral arms, stretching for light years. Andromeda's spiral arms are magnificent. They wind outward from the core in graceful curves, stretching for tens of thousands of light years. Each arm is a river of stars, gas and dust, glowing with the light of newborn suns and the pink haze of hydrogen nebulae. The arms aren't solid structures. They're density waves, regions where gas and dust accumulate, compressed by the galaxy's rotation. As material passes through these waves, it compresses, triggering star formation. The arms light up with young, hot stars, glowing blue and white, living fast and dying young. Behind them, older stars fade to yellow and red, and the arm dims, but the wave continues, sweeping around the galaxy, creating new generations of stars as it goes. Andromeda's spiral arms are temporary, constantly changing, yet always present. They're a feature of the galaxy's structure, a consequence of its rotation and the gravitational forces that shape it. Beautiful, dynamic, eternal, the giant among galaxies. Andromeda is big, really big. In fact, for a long time, astronomers thought it was the largest galaxy in the local group. The collection of galaxies that includes the Milky Way, Andromeda, and dozens of smaller companions. Recent measurements have complicated that picture. The Milky Way might have more dark matter, but Andromeda's visible disk is still larger. It stretches about 220,000 light-years across, more than twice the diameter of the Milky Way's visible disk. That's enormous. If you could see Andromeda's full extent in the night sky, it would appear several times larger than the full moon, a vast ghostly oval dominating the autumn constellations. But most of its disk is too faint to see without long exposure photography. What we see with our eyes is just the bright core and inner regions. The rest fades into darkness, invisible but present. Andromeda is a giant, a massive spiral dominating our local neighborhood, outshining nearly everything else nearby. The size comparison with the Milky Way. How does Andromeda compare to our home? In visible size, Andromeda wins. Its disk is larger, its spiral arms more extended. But when you account for dark matter, the invisible mass that surrounds all galaxies, the picture gets murky. The Milky Way might actually be more massive, with a larger dark matter halo. It's a close competition. Both galaxies are giants among spirals, each containing hundreds of billions of stars, but there are differences. Andromeda seems to have had a more violent past, consuming more satellite galaxies, building its mass through cannibalism. The Milky Way has been quieter, though not entirely peaceful. Andromeda's core is denser, its central black hole more massive. The Milky Way has a prominent bar structure. Andromeda's bar is less defined. They're similar galaxies, sisters in structure, but each with its own history, its own quirks. Comparing them teaches us about galactic diversity, about how even similar objects can have unique stories. The 1 trillion stars of Andromeda. Try to imagine a trillion, a million millions, 1,000 billions. It's a number so large it defies comprehension, and yet Andromeda contains about 1 trillion stars, each one a sun, some larger, some smaller, each with its own life story. Some are newborns, massive and blue, burning fiercely. Others are middle-aged, like our sun, stable and long-lived. And many are ancient, red giants, or white dwarfs, nearing the end of their existence. 1 trillion stars. If you counted one per second, it would take you over 31,000 years to count them all. And that's just the stars. Andromeda also contains countless planets, moons, asteroids, comets, nebulae, where new stars are forming, black holes left behind by dead stars, neutron stars, spinning in the darkness. It's an entire universe unto itself, a cosmic ecosystem of unimaginable complexity. When you look at Andromeda, you're seeing a trillion stories, all unfolding simultaneously across a canvas of light years. The sheer immensity of its disk. Andromeda's disk is vast. It stretches over 220,000 light years from edge to edge, a pancake of stars, gas, and dust, flattened by rotation. If you were inside Andromeda, looking out from a planet orbiting one of its stars, the night sky would be incredible. The galactic disk would arc overhead, a river of light stretching from horizon to horizon. Other stars would be closer together than in our neighborhood, the Milky Way seen from Earth. Nebula would glow in vivid colors. Globular clusters would hang like jewels in the sky. And if you were near the edge, looking back toward the core, you'd see the bright heart of the galaxy, a golden glow of ancient stars, so dense it would cast shadows at night. The disk is where most of Andromeda's visible matter resides. It's the stage on which the galaxy's drama plays out, the canvas on which billions of years of evolution are painted. Immense, beautiful, filled with light. The bright core at its center. At the heart of Andromeda lies its core, a dense concentration of stars packed so tightly they form a brilliant golden glow. Billions of stars, most of them old, red, and yellow. Stars that formed billions of years ago when the galaxy was young. This core is the gravitational center, the anchor around which the entire galaxy rotates. It's also incredibly bright, outshining the rest of the galaxy combined in some wavelengths. The core isn't uniform. There's structure within it, layers of stars at different densities, moving at different speeds, and at the very center, something even more extreme lurks. But we'll come to that in a moment. For now, just appreciate the core. It's ancient, dense, and blazing with the light of billions of suns. When you look at Andromeda through a telescope, the core is the first thing you see, a brilliant point of light, the beating heart of the galaxy, the supermassive black hole within. At the very center of Andromeda, buried deep within the bright core, there's a black hole, not just any black hole, but a supermassive one, weighing in at over 100 million times the mass of our sun. It's a gravitational monster, a point of infinite density from which nothing can escape. This black hole doesn't emit light. Nothing can escape from within its event horizon, but we can see its effects. Stars near the core orbit, incredibly fast, whipped around by the black hole's gravity. Gas spirals inward, heating as it falls, glowing in X-rays and ultraviolet light. The black hole is relatively quiet compared to some, not actively feeding on huge amounts of material, but it's there, dominating the central region, shaping the orbits of everything nearby. Every large galaxy seems to have one of these monsters at its heart. The connection between black holes and galaxy formation is one of astronomy's biggest mysteries. Andromeda's black hole is a piece of that puzzle, a window into the relationship between galaxies and the monsters they harbor. The heart that holds it together. The core of Andromeda isn't just bright, it's the gravitational heart that holds the entire galaxy together. Every star, every cloud of gas, every globular cluster orbits around this central region, held in place by the combined gravity of billions of stars and the supermassive black hole. Without the core, the galaxy would fly apart, its stars scattered into intergalactic space. The core is also the oldest part of Andromeda. It formed first, billions of years ago, from the merger of smaller protogalaxies. Over time, it grew, pulling in more stars, accreting mass, becoming denser. The core has witnessed Andromeda's entire history, from its formation to the present day. It's seen the galaxy grow through mergers, watched the spiral arms form and reform, overseeing the birth and death of countless generations of stars. The core is Andromeda's memory, its foundation, its heart, and it will outlast everything else, persisting long after the spiral arms have faded, long after the last star has died. The stars swirling around the core. Near Andromeda's core, stars move fast, incredibly fast. They whip around the central black hole at hundreds of kilometers per second, their orbits shaped by the immense gravity of the core. These stars are packed so closely that collisions are possible, though still rare even in such a dense environment. The stars closer to the core are older, red giants and red dwarfs, stars that have been there for billions of years. Farther out, younger stars mix in, adding blue and white light to the golden glow. The motion is chaotic at first glance, but there's order beneath. Stars follow orbits, ellipses and circles, prescribed by gravity's laws. Some orbits are stable, lasting for billions of years. Others are more eccentric, bringing stars close to the black hole before flinging them back out. It's a dance, a cosmic ballet, performed by billions of stars over timescales longer than human civilization. Beautiful, intricate, and entirely governed by gravity's invisible hand. The ancient globular clusters, scattered around Andromeda like moons around a planet, are globular clusters, ancient collections of stars, densely packed spheres containing hundreds of thousands of stars each. These clusters are old, really old. Some date back over 10 billion years, formed when Andromeda itself was young. They orbit the galaxy in wide, elliptical paths, traveling high above and below the galactic disk before swinging back through. Globular clusters are relics. They preserve the conditions of the early universe, containing stars with low metal content. Stars formed before generations of supernovae enriched the galaxy with heavy elements. By studying these clusters, astronomers learn about Andromeda's early history, about the conditions that existed when the galaxy was forming. Andromeda has hundreds of these clusters, maybe more than the Milky Way, another sign of its violent past. Each cluster is a time capsule, a window into the ancient cosmos, orbiting silently in the dark. The clouds of dust and gas. Between the stars of Andromeda lie vast clouds of dust and gas. These are the building blocks of future stars, the raw material from which new suns will be born. The gas is mostly hydrogen, with traces of helium and heavier elements. The dust is tiny particles, silicates and carbon compounds, smaller than grains of sand, but critical for star formation. These clouds are cold, just a few degrees above absolute zero, and dark. They block visible light, creating dark lanes in Andromeda's spiral arms, where stars seem absent. But in infrared light, these clouds glow with warmth, heated by nearby stars, and within them, gravity is working. The densest parts of the clouds are collapsing, pulling themselves together, heating up. Eventually, they'll ignite, forming new stars. The clouds of Andromeda are nurseries, quiet places where the future is being shaped. Without them, star formation would stop, and the galaxy would slowly fade. The birthplaces of new stars. Deep within Andromeda's dust clouds, new stars are being born. The process begins with collapse, a cloud of gas, disturbed by a passing shock wave, or the gravity of nearby stars begins to contract. As it collapses, it fragments, breaking into smaller clumps. Each clump continues to collapse, growing denser and hotter. Eventually, the center reaches temperatures high enough for nuclear fusion to ignite. A star is born. This process happens constantly in Andromeda. Thousands of stars forming every year. Most are small red dwarfs that will burn for trillions of years. Some are medium-sized, like our sun, and a few are massive, blue giants that will live fast and die young in spectacular supernovae. These birthplaces are hidden, shrouded in dust, invisible to optical telescopes, but infrared and radio observations pierce the veil, revealing the cradles where Andromeda's future generations emerge. Star formation is the lifeblood of the galaxy. the process that keeps it alive, vibrant, and evolving. The pink glow of hydrogen nebulae. Look at a color image of Andromeda, and you'll notice pink patches scattered along the spiral arms. These are hydrogen nebulae, clouds of gas, glowing in the light of nearby young stars. The stars, hot and blue, emit ultraviolet radiation that ionizes the hydrogen, stripping away electrons. When the electrons recombine with hydrogen nuclei, they emit light at a specific wavelength, a deep red color called His alpha. This gives the nebulae their distinctive pink glow. These regions mark sites of recent star formation. Wherever you see pink, young stars have recently been born, and their radiation is lighting up the surrounding gas. The nebulae are beautiful, but they're temporary. Over time, the stars will blow the gas away with their stellar winds, dispersing the nebula, leaving behind open clusters of stars. The pink glow fades, but the stars remain, a generation born from the gas, now shining on their own. The blue light of young star clusters. In Andromeda's spiral arms, you'll find patches of blue light. These are young star clusters, collections of massive stars that form together from the same cloud of gas. These stars are hot, tens of thousands of degrees at their surfaces, and they burn blue and white. They're incredibly luminous, each one shining with the light of thousands of suns, but they won't last long. Massive stars have short lives, only a few million years before they exhaust their fuel and explode as supernovae. The blue light is a sign of youth, of recent star formation, of a galaxy still actively creating new generations. These clusters are transient. In cosmic terms, they'll vanish in the blink of an eye, but while they exist, they dominate the light of the spiral arms, turning regions of the galaxy into brilliant blue beacons. They're Andromeda's youth, its vitality, proof that even an ancient galaxy can still be young at heart. The golden core of ancient suns. While the spiral arms glow blue with young stars, the core of Andromeda shines golden. This is the light of ancient suns, stars billions of years old, long past their youth. Most are red giants and red dwarfs, cooler stars that emit light in the yellow and red parts of the spectrum. Mixed together, they create a warm golden glow, the signature of an old stellar population. These stars formed when Andromeda was young, back when the universe itself was a fraction of its current age. They've witnessed the galaxy's entire history. They've seen it grow through mergers, watched the spiral arms form, orbited the core billions of times, and they'll continue to shine for billions more years, slowly fading as they exhaust their fuel, eventually becoming white dwarfs, stellar corpses cooling in the dark. The golden core is Andromeda's memory, its past made visible, a reminder that galaxies, like stars, have life cycles that stretch across unimaginable spans of time. The star factories in its spiral arms. Andromeda's spiral arms are factories, not in the industrial sense, but in the cosmic one. They're where stars are made, churned out in vast quantities, generation after generation. The arms are density waves, regions where gas and dust pile up, compressed by the galaxy's rotation. In these dense regions, conditions are right for collapse, for star formation. Clouds fragment, clumps heat up, stars ignite. The process is continuous, ongoing, relentless. As long as there's gas in the arms, stars will form. And Andromeda has plenty of gas, enough to keep forming stars for billions of years. The star factories aren't evenly distributed. Some regions are more active than others, creating massive star clusters, lighting up the arm with blue light and pink nebulae. Other regions are quieter, forming only small stars, barely visible against the background. But collectively, the spiral arms are Andromeda's engine of renewal, the mechanism by which it stays young despite its ancient age. The interstellar winds that shape its form. Stars don't just sit quietly in Andromeda. They breathe. Massive stars emit powerful stellar winds, streams of charged particles that blow outward at thousands of kilometers per second. When these stars explode as supernovae, they release even more energy, sending shockwaves rippling through the surrounding gas. These winds and explosions shape Andromeda's structure. They carve bubbles in the gas clouds, clearing space around star-forming regions. They compress nearby clouds, sometimes triggering new rounds of star formation. They inject energy into the interstellar medium, heating the gas, preventing it from collapsing too quickly. And they enrich the gas with heavy elements, carbon and oxygen and iron, elements forged in stellar cores and scattered through space. The interstellar winds are invisible, but their effects are everywhere. They sculpt the galaxy, shape its spiral arms, regulate its star formation. Andromeda is shaped not just by gravity, but by the collective breath of its stars, the motion of stars around the center. Every star in Andromeda is moving, orbiting the galactic center in vast, slow circles that take hundreds of millions of years to complete. Stars near the core move faster, whipped around by the intense gravity. Stars farther out move more slowly, their orbits gentler, more relaxed. But all of them are moving, all following paths dictated by gravity. The motion isn't perfect. Stars don't orbit in neat circular paths like planets around a sun. Their orbits are elliptical, tilted, sometimes chaotic. Stars can pass close to each other, their paths perturbed by gravitational interactions. Some stars are ejected entirely, flung out of the galaxy by close encounters with the central black hole or by gravitational slingshots. But most stay, orbiting endlessly, part of the galactic dance. By studying these motions, astronomers map Andromeda's mass distribution, revealing not just the visible stars and gas, but the dark matter that dominates the galaxy's gravitational field. The hidden patterns of galactic rotation. Andromeda rotates. The entire galaxy spins like a vast pinwheel, completing one rotation every few 100 million years. But the rotation isn't uniform. Stars near the core orbit faster than stars farther out, which is what you'd expect from gravity. Except there's a problem. When astronomers measure the rotation speeds at different distances from the core, they find something strange. Stars in the outer regions are moving faster than they should, much faster. There's not enough visible mass to account for their speed. They should fly off into space, escaping the galaxy's gravity, but they don't. Something invisible is holding them in, providing extra gravitational pull. That something is dark matter, an invisible halo surrounding Andromeda, containing far more mass than all the visible stars and gas combined. The rotation curve, the graph of orbital speed versus distance, reveals this hidden mass, a pattern that points to one of the universe's greatest mysteries. The evidence of dark matter. Andromeda is surrounded by dark matter. You can't see it. It doesn't emit light, doesn't interact with normal matter, except through gravity. But we know it's there because of its effects. The rotation speeds of stars, the motions of globular clusters, the gravitational lensing of background galaxies, all point to an enormous invisible halo, extending far beyond Andromeda's visible edge. This dark matter makes up most of the galaxy's mass. Estimates suggest it outweighs the visible stars and gas by a factor of 10 or more. Without it, Andromeda wouldn't exist. The gas clouds that formed the galaxy would never have collapsed. The disk would fly apart. The spiral structure would dissolve. Dark matter is Andromeda's foundation, the invisible scaffolding that holds everything together. And yet, we still don't know what it is. Particles? Modified gravity? Something else entirely? Andromeda's dark matter halo is evidence of one of physics' biggest unsolved puzzles, the halo that extends beyond its edge. Beyond Andromeda's bright disk, there's a halo, not the dark matter halo, though that's there too, but a halo of stars and globular clusters, scattered in a vast sphere around the galaxy. These stars are faint, old, metal-poor relics from Andromeda's early days. They orbit the galaxy in wide, elliptical paths, far from the disk, part of the galaxy but separate from its main structure. This stellar halo extends for hundreds of thousands of light years, far beyond where the spiral arms fade into darkness. It's a relic, a fossil record of Andromeda's formation. When smaller galaxies merged to form Andromeda, some of their stars were scattered into wide orbits, creating the halo. By studying the halo's stars, astronomers trace Andromeda's history, reconstructing the mergers and collisions that built it. The halo is faint, hard to see, but it's there, a ghostly shell surrounding one of the universe's grandest spirals, the invisible mass holding it together. Most of Andromeda's mass is invisible. The stars you see, the gas clouds, the dust lanes, all of it combined makes up only a fraction of the galaxy's total mass. The rest is dark matter, an unknown substance that doesn't emit or absorb light, detectable only through its gravitational effects. This invisible mass forms a vast halo around Andromeda, extending far beyond the visible disk, perhaps hundreds of thousands or even millions of light years from the center. Without it, Andromeda wouldn't hold together. The outer stars would escape, the spiral arms would unwind, the entire structure would dissolve into the void. Dark matter is the glue that binds galaxies, the foundation upon which visible matter builds its structures. We don't know what it is. Particles we haven't discovered yet? Some modification to our understanding of gravity? The answer remains elusive. But in Andromeda, as in every galaxy, dark matter dominates. It shapes the rotation curve, influences the orbits of satellite galaxies, and provides the gravitational scaffolding for everything we see. Invisible, mysterious, essential. The streams of stars in orbit. If you look carefully, Andromeda's outer regions, you'll find something strange. Streams of stars, long tendrils, stretching across space, arcing around the galaxy like ribbons caught in the wind. These aren't random, they're the remnants of smaller galaxies that Andromeda consumed. When a dwarf galaxy falls into Andromeda's gravitational well, tidal forces tear it apart, stretching it into a long stream. The stars that once formed a coherent galaxy are scattered along their orbit, creating these stellar streams. Some streams are recent, still clearly visible, their stars clustered relatively close together. Others are ancient, stretched so thin they're barely detectable, their stars scattered across vast distances. These streams are evidence of Andromeda's violent past, proof that it grew through cannibalism, devouring its smaller neighbors. By mapping these streams, astronomers reconstruct Andromeda's history, identifying which galaxies it consumed and when. The streams are scars, memories of ancient collisions written in starlight, the remnants of ancient collisions. Andromeda's history is violent. It didn't form peacefully, gradually accumulating gas and dust. It grew through collisions, through mergers with other galaxies, each one adding mass, restructuring the disk, triggering bursts of star formation. The evidence is everywhere. The stellar streams, the disturbed gas in the outer regions, the off-center structures in the core. Even the disk itself shows signs of past trauma, warps and asymmetries that suggest relatively recent mergers. Some of these collisions happened billions of years ago, their effects now faded, visible only in subtle features. Others are more recent, cosmically speaking, their scars still fresh. Andromeda is a cannibal, a galaxy that has consumed dozens of smaller companions over its lifetime, and it's still doing it. Right now, there are dwarf galaxies falling into Andromeda, being torn apart by tidal forces, their stars joining the growing halo. Andromeda's growth continues, driven by the same violent processes that built it in the first place. The galaxies that Andromeda has consumed. Over billions of years, Andromeda has consumed dozens of smaller galaxies. Most were dwarfs, tiny collections of stars that wandered too close and were swallowed whole. Their stars now orbit within Andromeda's halo, scattered and anonymous, their original galaxies erased from existence. But some of the victims were larger, mid-sized galaxies that fought back, distorting Andromeda's structure before being absorbed. The largest merger, may have happened relatively recently, within the last few billion years. Astronomers have found evidence of a massive collision that restructured Andromeda's disk, created the strange off-center features in its core, and triggered a burst of star formation. That collision added enormous mass to Andromeda, helping make it the giant it is today. The consumed galaxies are gone, their individual identities lost, but their stars remain, now part of Andromeda, contributors to its trillion-star population. Cannibalism is how galaxies grow, and Andromeda is a master at it, the cannibal of the local group. Within our local cosmic neighborhood, the local group of galaxies, Andromeda is the dominant predator. It's the largest, most massive galaxy, and it's been feeding on its neighbors for billions of years. The Milky Way has also consumed dwarf galaxies, but Andromeda seems more voracious, more efficient at the game of galactic cannibalism. Its mass and gravity give it an advantage. Smaller galaxies are drawn to it, unable to escape its pull, destined to be torn apart and absorbed. This process will continue. There are still dwarf galaxies orbiting Andromeda, and eventually they'll fall in. And then there's the Milky Way. In about 4 billion years, Andromeda and our galaxy will collide, the ultimate act of cannibalism. Two giants merging, creating something entirely new. Andromeda's cannibalistic nature isn't unique. Most large galaxies grow this way, but it's particularly evident here, written in the stellar streams and distorted structures that surround it. The trails of light left behind. The stellar streams around Andromeda aren't uniform. They have structure, brightness variations, clumps where stars are more concentrated. These are the trails left by disrupted galaxies, breadcrumbs, showing the path of each victim as it orbited Andromeda before being torn apart. By mapping these trails, astronomers can reconstruct the orbits of the consumed galaxies, figuring out where they came from, how fast they were moving when they were destroyed. It's like cosmic forensics, piecing together ancient crimes from the evidence left behind. The trails glow faintly, visible only in deep, long exposure images, or in the data from sensitive surveys, but they're there, wrapping around Andromeda in complex patterns, each one telling the story of a galaxy that no longer exists. These trails of light are history made visible, the memories of Andromeda's violent past, preserved in the positions and motions of scattered stars. The satellite galaxies that circle it. Andromeda isn't alone. It's surrounded by a family of smaller satellite galaxies, bound to it by gravity, orbiting like moons around a planet. There are dozens of these satellites, ranging from tiny dwarfs with just a few million stars to larger galaxies like M32 and M110, which are visible in amateur telescopes. These satellites are separate galaxies, each with its own structure, its own population of stars, but they're dominated by Andromeda's gravity, forced to orbit the giant, unable to escape. Some of these satellites will eventually be consumed, adding to Andromeda's mass. Others might survive for billions of years, maintaining their independence through sheer distance or favorable orbits. These satellites are important. They're laboratories for studying galaxy formation, evolution, and the effects of gravitational interactions, and they're part of Andromeda's ecosystem, contributors to the complex web of gravity and motion that defines the local group. The companions, Mir 32 and M110. Two of Andromeda's satellites are particularly notable, Men 32 and M110. Men 32 is a compact elliptical galaxy, small but dense, packed with old stars. It sits very close to Andromeda's disk, and some astronomers think it's actually passing through the disk, its structure being distorted by the interaction. MEM 32 might have once been much larger, a spiral galaxy like Andromeda itself, but gravitational interactions stripped away its outer regions, leaving only the dense core. MEM 110 is a dwarf elliptical, larger and more diffuse than M32, sitting farther from Andromeda's center. It shows signs of recent star formation, unusual for an elliptical galaxy, possibly triggered by its interactions with Andromeda. Both M32 and M110 are visible in the same telescopic field of view as Andromeda, making them popular targets for amateur astronomers. Their companions, orbiting the giant, forever bound to its gravitational embrace. The dance of gravity among them. Andromeda and its satellites are locked in a gravitational dance. Each satellite orbits the central galaxy, but the satellites also influence each other. Their combined gravity, creating subtle perturbations in their orbits. Some satellites orbit close together, their paths intertwined. Others are solitary, following wide, lonely orbits, far from the main group. The dance is slow, each orbit taking hundreds of millions of years to complete, but it's not static. Over time, orbits decay, satellites drift inward, collisions become inevitable. The dance is also destructive. Tidal forces stretch and compress the satellites, sometimes triggering star formation, sometimes tearing them apart entirely. It's a complex, dynamic system, constantly evolving, constantly changing. By studying this dance, astronomers learn about gravitational interactions, about how systems of multiple bodies behave over cosmic timescales. Andromeda and its satellites are a laboratory, a natural experiment in orbital dynamics, playing out in real time. The web of interacting galaxies. Andromeda isn't just interacting with its satellites, it's part of a larger web of gravitational relationships that includes the Milky Way and dozens of other galaxies in the local group. These galaxies aren't isolated, they influence each other through gravity, subtle tugs that alter orbits, trigger star formation, and shape galactic structure. Andromeda and the Milky Way are the two dominant members of this group, and their mutual gravity dominates the local dynamics. They're approaching each other, drawn together by billions of years of gravitational attraction. The smaller galaxies in the group are affected too, their motions influenced by the two giants. Some orbit Andromeda, some orbit the Milky Way, and some are caught between, destined to be pulled into one or the other. This web of interactions will culminate in the merger of Andromeda and the Milky Way, an event that will reshape the entire local group. The dark bridges of gas and dust. Between Andromeda and the Milky Way, there might be bridges, tendrils of gas and dust, stretching across the intergalactic void, connecting the two galaxies. These bridges would be incredibly faint, barely detectable even with sensitive instruments. But there's some evidence they exist. Traces of hydrogen gas scattered between the galaxies, possibly stripped from smaller galaxies, passing between them, or perhaps material exchange during past close approaches. These dark bridges are controversial. Not all astronomers are convinced they exist, but if they do, they're evidence that Andromeda and the Milky Way have been interacting for billions of years, that their influence on each other extends far beyond their visible edges. The bridges would be precursors to the merger, early signs of the gravitational connection that will eventually pull the two galaxies together. Dark, cold, almost invisible, but potentially crucial to understanding the relationship between our two galactic giants. The light that has traveled 2 million years. Every photon from Andromeda is ancient. It began its journey over 2 million years ago, when Earth was a very different place. Early humans were just beginning to appear. Africa was their only home, and the ice ages were shaping the planet's climate. While those photons crossed the void, entire species evolved and went extinct. Continents shifted, mountains rose and eroded, and finally, after all that time, the light arrives. It enters our telescopes, strikes our cameras, and gets recorded as data. That light carries information. It tells us about Andromeda's temperature, its chemical composition, its motion through space. It's a message from the past, a snapshot of a galaxy as it was in the distant age before humans. When we study Andromeda, we're not seeing it as it is now, we're seeing its history. The galaxy has continued to evolve, to change, but we'll never see those changes until millions of years in the future. Andromeda's light is a time capsule, the distance that connects our galaxies. 2.5 million light years. That's the distance separating Andromeda and the Milky Way. It's vast, incomprehensible, a gulf so wide that light itself takes millions of years to cross it. And yet, in cosmic terms, it's nothing. Andromeda is our closest large galactic neighbor, practically touching us compared to most galaxies. That proximity creates a connection. We're bound by gravity, approaching each other, destined to merge. We share a common space, a region of the universe where we're the dominant structures, and we can study each other. Andromeda reveals things about our own galaxy that we can't see from inside it. By studying its structure, its star formation, its history, we learn about how galaxies like the Milky Way behave. The distance separates us, yes, but it also connects us, making Andromeda not just a distant object, but a neighbor, a companion, a twin galaxy sharing our corner of the cosmos. The speed of its approach toward us. Andromeda is moving toward us. Right now, at this very moment, it's rushing through space at about 110 kilometers per second, closing the gap between our galaxies. That's over 200,000 miles per hour, incredibly fast by human standards. But space is vast, and even at that speed, it will take billions of years for Andromeda to reach us. The approach is inevitable. Gravity has been pulling the two galaxies together for billions of years, and there's no stopping it now. We're on a collision course, a slow-motion crash that will play out over billions of years. But collision is misleading. Galaxies are mostly empty space, and when Andromeda and the Milky Way merge, very few stars will actually collide. Instead, the two galaxies will pass through each other, their structures distorting, their spiral arms stretching, until eventually they settle into a new configuration, a single, unified galaxy. The future collision with the Milky Way. In about 4 billion years, Andromeda and the Milky Way will collide. It won't be a sudden impact. It will be a slow, graceful merger, taking billions of years to complete. The galaxies will approach each other, their gravitational influence growing stronger. The spiral arms will begin to distort. Pulled by tidal forces, star formation will ignite across both galaxies as gas clouds collide and compress. The night sky will transform, Andromeda growing larger and larger until it dominates the view, a vast spiral stretching across the heavens. The galaxies will pass through each other once, twice, maybe more, their structures becoming increasingly tangled. Eventually, the spiral shapes will be destroyed, the ordered rotation disrupted, and finally, after billions of years of chaos, the two galaxies will settle into a new form, a single, massive elliptical galaxy. The merger is inevitable, and it will change everything. The merging of two spiral giants. When Andromeda and the Milky Way merge, two of the universe's most beautiful structures will be destroyed. The spiral arms, with their delicate curves and bright star-forming regions, will be torn apart. The ordered rotation will dissolve into chaos. Stars will be scattered into new orbits, some flung far from the galactic center, others pulled inward. Gas clouds will collide, triggering massive bursts of star formation, creating millions of new stars in a relatively short time. The merger will be violent, but not in the way you might imagine. Individual stars almost certainly won't collide. They're too far apart, but the large-scale structure will be completely rearranged, and from the chaos, something new will emerge. A massive, elliptical galaxy, perhaps twice the size of either original galaxy, filled with old stars, its spiral structure replaced by a smooth, featureless glow. The merger will create a new galaxy from two old ones. Destruction and creation, intertwined. the galactic ballet of the future. The merger of Andromeda and the Milky Way will be a ballet, a cosmic dance performed over billions of years. Choreographed by gravity, the galaxies will approach, circling each other like dancers, drawn together, but not yet touching. They'll pass close, their spiral arms reaching toward each other, pulled by tidal forces. Then they'll separate, moving apart, only to swing back around for another pass. Each pass will bring them closer, their orbits decaying, their structures becoming more distorted. Long streamers of stars will be pulled out of both galaxies, stretching across space like ribbons. Gas clouds will collide, igniting bursts of star formation that light up the dance floor. And slowly, over billions of years, the two galaxies will spiral inward, losing energy, until finally they merge completely. It's a ballet that won't have any observers, at least not human ones, but it will be beautiful nonetheless. A dance of giants, performed in the darkness of space. The night sky 4 billion years from now. Imagine standing on Earth, if it still exists, 4 billion years from now. The night sky would be unrecognizable. Andromeda would no longer be a faint smudge. It would dominate the sky, a vast spiral stretching from horizon to horizon, its arms clearly visible, individual star clusters shining like jewels. As the merger progressed, the sky would become even stranger. Multiple bright cores as the galaxy's centers orbit each other. Long streamers of stars arcing across the darkness. The Milky Way's disk, distorted and warped, visible as a glowing band, but no longer recognizable. Regions of intense star formation, glowing pink and blue, scattered throughout the sky. It would be spectacular, terrifying, and beautiful. The constellations would be gone, replaced by a chaotic swirl of light. But for anyone alive to see it, it would be the greatest show in the universe. A reminder that galaxies, like everything else, have life cycles that involve birth, growth, and transformation. The collision that will create Milkomeda. Astronomers have already named the galaxy that will result from the merger, Milkomeda. The combination of Milky Way and Andromeda, simple and descriptive. Milkomeda will be massive, a giant elliptical galaxy containing the stars of both its parents. It will be one of the largest galaxies in the local group, dominating the neighborhood. The spiral structure will be gone, replaced by a smooth distribution of stars, most of them old and red, their star-forming days long past. But Milkomeda won't be lifeless. It will still contain gas, still form some stars, though at a much slower rate than the spirals that created it. It will have a supermassive black hole at its center, formed from the merger of Andromedas and the Milky Way's central black holes, and it will have a vast halo of stars, globular clusters, and dark matter extending far into space. Milkomeda will be the legacy of two great galaxies, a monument to their collision, a new chapter in cosmic evolution, the new shape of a unified galaxy. Milkomeda will look very different from its parent galaxies. Instead of a flat disk with spiral arms, it will be roughly spherical or elliptical, a smooth blob of starlight with no clear structure. This is typical for galaxies that form through mergers. The collision disrupts the ordered rotation of the spiral disks, scattering stars into random orbits. The result is an elliptical galaxy, where stars move in all directions, their collective motion canceling out any net rotation. Elliptical galaxies are common in the universe, especially in dense galaxy clusters, where mergers are frequent. Milkomeda will join their ranks. It won't be as visually striking as a spiral, lacking the dramatic arms and dust lanes, but it will have its own beauty, a soft, golden glow, the combined light of trillions of old stars, fading gradually from a bright core to a dim edge. Simple, elegant, and permanent, barring future mergers, Milkomeda will maintain this shape for the rest of cosmic time. The fate of stars during the merge. What happens to individual stars during the merger? Surprisingly, Most will be fine. Stars are so far apart that direct collisions are incredibly rare, even when two galaxies merge. The Sun, if it still exists in 4 billion years, will probably survive the collision unscathed, though its orbit will change dramatically. It might be flung far from the galactic center, out into the halo, or it might be pulled inward, closer to the core, but it won't collide with another star. The real danger is more subtle. The merger will disrupt the solar system's orbit, exposing it to different regions of the galaxy, possibly bringing it closer to areas of intense radiation or star formation. And there's always a small chance, incredibly small but non-zero, that the Sun could be ejected entirely, flung out of the merged galaxy into intergalactic space. But most stars will simply find themselves in new orbits, part of a new galaxy, their individual lives largely unchanged by the cosmic catastrophe around them. The gravity that will rewrite the sky. During the merger, gravity will reshape everything. The familiar constellations will dissolve as stars move into new positions. The Milky Way's band of light, which has been a fixture of Earth's night sky for all of human history, will change beyond recognition, eventually disappearing entirely as the disk is destroyed. Stars that were once far away will be pulled close, brightening the night sky. Others will be pushed farther away, fading from view. The gravitational interactions will be complex, chaotic, impossible to predict in detail. Some stars will gain energy, their orbits expanding. Others will lose energy, spiraling inward. The night sky will be rewritten, line by line, star by star, over billions of years. And when the merger is complete, when Milky Way settles into its new configuration, the sky will be utterly different. A new stellar arrangement, unfamiliar and strange. The result of gravity's patient work over cosmic timescales. The birth of new stars. From chaos. The merger won't just destroy structure. It will also create. When gas clouds from the two galaxies collide, they'll compress, triggering intense bursts of star formation. These starbursts will create millions of new stars in a relatively short time, perhaps a few 100 million years. The new stars will be hot and blue, massive and short-lived, burning fiercely before exploding as supernovae. These starbursts will light up regions of the merging galaxies, creating brilliant patches of blue and pink light visible across vast distances. It's a final act of creation before the galaxies settle into old age. After the merger is complete, after Milky Way has formed, star formation will slow dramatically. Most of the gas will have been used up or heated to temperatures too high for star formation. Milky Way will be a red and dead galaxy, filled mostly with old stars, its days of vigorous star formation behind it. But the starburst during the merger will be spectacular, a last blaze of youth. The black holes that will join as one. At the centers of both Andromeda and the Milky Way lie supermassive black holes. When the galaxies merge, these black holes will eventually merge too, creating a single, even more massive black hole at the heart of Milky Way. But this merger won't happen immediately. First, the two black holes will orbit each other, circling at the center of the merged galaxy. Over time, they'll spiral inward, losing energy to gravitational radiation, drawing closer and closer. Eventually, they'll be so close that nothing can stop them. They'll merge in a violent event that releases enormous amounts of energy in the form of gravitational waves, ripples in space-time itself that will spread across the universe. This black hole merger will be one of the most energetic events in the cosmos, briefly outshining entire galaxies in gravitational wave emission. And when it's over, Milky Way will have a single supermassive black hole at its core, billions of times the mass of the Sun, the gravitational heart of the new galaxy. The calm that follows the collision. After billions of years of chaos, Milky Way will finally settle. The violent interactions will cease. The gas clouds will have been used up or dispersed. Star formation will slow to a trickle. The stars will find stable orbits in the new configuration, their paths no longer disturbed by the ongoing merger. and a calm will descend. Milkomeda will enter a quiet phase, an old age that will last for trillions of years. The galaxy will slowly fade as its stars exhaust their fuel and die, one by one, over unimaginable stretches of time. But that fading will be slow, gentle, almost imperceptible. For billions of years after the merger, Milkomeda will still be bright, still filled with stars, still a major structure in the local group. The calm after the storm will be long-lasting, a cosmic rest after the exertion of collision and merger. Milkomeda will persist, a monument to the two galaxies that created it. The final elliptical galaxy that remains. Milkomeda will be an elliptical galaxy. And elliptical galaxies are the endpoints of galactic evolution. They're the final form, the state galaxies reach after all the mergers are done. All the gas is used up. All the spiral structure is destroyed. Milkomeda will join the countless other elliptical galaxies scattered throughout the universe. Each one, a similar story of merger and transformation. It will be massive, bright, and relatively featureless. A smooth distribution of old stars, and it will be stable. Without ongoing star formation or major interactions, Milkomeda will maintain its elliptical shape for the rest of cosmic time, trillions of years into the future. Long after the last star has formed, long after most stars have died, Milkomeda will still be there, slowly fading, but still recognizable. A relic of an earlier epoch, a monument to the age when galaxies merged and star formation was still possible. The final form, eternal and unchanging. The cycles of galactic creation and death. Galaxies have life cycles, just like stars. They're born from clouds of gas in the early universe. They grow through accretion and mergers. They form stars, create heavy elements, evolve over time, and eventually, they reach a final state, an endpoint where major evolution ceases. Andromeda and the Milky Way are in their middle age, still forming stars, still evolving, but past the vigorous youth of the early universe. Their merger will be a kind of death, the end of two spiral galaxies, but it will also be a rebirth, the creation of Milkomeda, and Milkomeda itself will eventually age, its star formation ceasing, its light slowly fading. In the far future, in the unimaginably distant time when the universe is old and cold, Milkomeda will be a ghost, a collection of stellar remnants orbiting in the darkness. But that's trillions of years away. For now, Andromeda and the Milky Way are alive, vibrant, and heading toward their rendezvous with destiny. The history of Andromeda's formation. Andromeda wasn't always a grand spiral. It started small, as a collection of smaller protogalaxies in the early universe. These were clumps of dark matter and gas, pulled together by gravity in the chaotic aftermath of the Big Bang. Over time, these protogalaxies merged, combining their mass, growing larger. The first stars formed, massive blue giants that lived fast and died young, enriching the gas with heavy elements. More mergers followed, each one adding mass, structure, complexity. Slowly, over billions of years, Andromeda took shape, a disk formed from the rotating gas, flattened by centrifugal force. Spiral arms emerged from density waves. In the disk, a central bulge formed from early mergers, and the supermassive black hole at the core grew, fed by infalling gas and smaller black holes from consumed galaxies. Andromeda's history is written in its structure, in the streams and shells and asymmetries that record ancient collisions. It's a history of violence, of growth through cannibalism, of gradual assembly over cosmic time. The ancient protogalaxies that merged, the galaxies that merged to form Andromeda, are long gone, their individual identities erased. But we can infer something about them from the evidence they left behind. The stellar halo contains stars with varying chemical compositions, suggesting they came from multiple sources. The age distribution of globular clusters shows multiple formation episodes, consistent with a series of mergers. The structure of the disk shows signs of past disruptions, warps, and asymmetries that point to relatively recent collisions. By piecing together these clues, astronomers reconstruct Andromeda's family tree, identifying the approximate number and sizes of the protogalaxies that merged to create it. There may have been dozens of significant mergers, hundreds of minor ones. Each one added something: stars, gas, dark matter, building Andromeda into the giant it is today. Those ancient protogalaxies are Andromeda's ancestors, the building blocks from which it was assembled, gone but not forgotten, remembered in the structure they helped create. The birth of its first stars. Andromeda's first stars were unlike anything we see today. They formed in the early universe, from gas that was almost entirely hydrogen and helium, lacking the heavier elements that exist now. These first stars were massive, hundreds of times the mass of the Sun, burning incredibly hot and bright. They lived only a few million years before exploding as supernovae, scattering the first heavy elements, carbon, oxygen, iron, into the surrounding gas. These elements would become part of the next generation of stars, enriching them, allowing planets to form. Andromeda's first stars are all gone now, their lives too short to survive until the present, but their legacy remains. Every heavy element in Andromeda, every atom of carbon in its organic molecules, every iron atom in potential planets, was forged in the cores of these ancient stars and scattered by their deaths. The first stars lit up Andromeda's darkness and seeded it with the elements of life. The evolution over billions of years. Andromeda has been evolving for over 10 billion years, perhaps longer. In that time, it's undergone countless changes. Star formation rates have risen and fallen, driven by the availability of gas and the frequency of mergers. The spiral structure has formed, dissolved, and reformed, shaped by density waves and gravitational interactions. The central black hole has grown from a modest seed to a monster billions of times the Sun's mass. The stellar population has aged, early massive stars dying off, replaced by longer-lived low-mass stars and the remnants of the dead. The halo has grown through accretion, capturing stars from disrupted satellites. And through it all, Andromeda has maintained its basic identity as a spiral galaxy, despite the violence of its history. But that will change. The merger with the Milky Way will transform Andromeda beyond recognition, ending its life as a spiral and beginning its existence as an elliptical. Evolution continues, always, until the end of time. The chemical elements in its stars. The stars of Andromeda contain the entire periodic table: hydrogen and helium from the Big Bang, carbon, nitrogen, and oxygen forged in the cores of stars like the Sun, iron, nickel, and other heavy elements created in supernova explosions. Even gold, platinum, and uranium formed in the violent collisions of neutron stars. Every element heavier than helium was created in stars or stellar explosions, then scattered into space, incorporated into new generations of stars and planets. By studying the spectra of Andromeda's stars, astronomers measure these elemental abundances, learning about the galaxy's chemical evolution. Stars in the halo are metal-poor, born early, when few heavy elements existed. Stars in the disk are metal-rich, enriched by generations of stellar deaths. The chemical elements are a record, a history written in atoms, showing how Andromeda has evolved over billions of years. The clues about the early universe. Andromeda's oldest stars are windows into the early universe. They formed when the cosmos was young, when conditions were different from today. By studying these ancient stars, astronomers learn about the universe's chemical composition in its youth, about the first generations of star formation, about the processes that turned the simple gas of the Big Bang into the complex structures we see today. These stars have low metallicity, meaning they contain few heavy elements, reflecting the composition of the early universe before generations of stars had enriched the gas. They're also old, often over 10 billion years, placing constraints on when galaxy formation began. Some of Andromeda's globular clusters may be even older, relics from the very first epoch of star formation. Every ancient star in Andromeda is a messenger from the past, carrying information about conditions billions of years ago. They're invaluable, irreplaceable archives of cosmic history. The role of supernovae in enriching matter. Supernovae have played a crucial role in Andromeda's evolution. These stellar explosions are among the most energetic events in the universe, briefly outshining entire galaxies, but they're more than just spectacular. They're essential for galactic evolution. When a massive star explodes as a supernova, it scatters its enriched material, heavy elements forged in its core, into the surrounding gas. This material mixes with the interstellar medium, enriching it, raising its metallicity. The next generation of stars forms from this enriched gas, incorporating the heavy elements into their composition. Over billions of years, countless supernovae have enriched Andromeda's gas, increasing its metal content from nearly zero to the current levels. Without supernovae, there would be no heavy elements, no rocky planets, no life as we know it. Supernovae are Andromeda's alchemists, transforming simple elements into complex ones, enabling the chemical diversity that makes the universe interesting. The stellar populations within Andromeda. Andromeda contains multiple stellar populations, groups of stars with different ages, chemical compositions, and spatial distributions. The oldest population is in the halo and bulge, stars formed early in the galaxy's history, metal poor and red. The disk contains a mix of ages, from ancient stars to newborns, with higher metal content, reflecting billions of years of enrichment. The spiral arms are dominated by young blue stars, formed recently from gas compressed by density waves. By studying these populations, astronomers reconstruct Andromeda's star formation history, learning when and where stars formed, how the rate has changed over time. The stellar populations are like tree rings, each layer recording a different epoch in the galaxy's life. They show that Andromeda's star formation hasn't been constant. There have been bursts, possibly triggered by mergers and quieter periods. The populations are a record, preserved in starlight, of Andromeda's long and complex history. The difference between its core and its arms. Andromeda's core and spiral arms couldn't be more different. The core is dense, packed with old stars, glowing golden and red. Star formation there ceased billions of years ago, and the stellar population has aged into quiet retirement. The arms, by contrast, are young and vibrant, glowing blue and pink with new stars and nebulae. Star formation is active, ongoing, creating new generations constantly. The core is stable, unchanging, over billions of years. The arms are dynamic, constantly restructured by density waves and stellar evolution. The core is dominated by gravity, its stars bound tightly by the central black hole's immense mass. The arms are shaped by rotation, their spiral pattern emerging from the galaxy's spin. These differences reflect Andromeda's history. The core formed first, through mergers, and has been quiescent since. The arms formed later, as the disk settled into rotation and continued to evolve. Two regions, one galaxy, each telling a different part of the story, the hidden black hole activity over time. Andromeda's central black hole is relatively quiet now, not actively feeding on large amounts of material, but it wasn't always this way. In the past, when Andromeda was younger, the black hole was likely more active, possibly a quasar, blazing with the light of infalling gas heated to millions of degrees. Evidence of this past activity is subtle but present. The structure of the core shows signs of disruption, possibly from energetic outflows when the black hole was feeding. X-ray observations reveal hot gas near the center, remnants of past heating, and the double nucleus, a strange feature where the core appears to have two bright peaks, might be evidence of a past merger between two black holes. Andromeda's black hole has a history, periods of violent feeding, followed by quiescence, cycles driven by the availability of gas. Right now, we're in a quiet phase, but that could change. When Andromeda merges with the Milky Way, fresh gas will funnel toward the center, and the black hole will feed again, possibly becoming a bright quasar once more. The tidal streams of disrupted galaxies. Around Andromeda, astronomers have mapped dozens of tidal streams, long ribbons of stars stretched across space. These are the remnants of dwarf galaxies that wandered too close or torn apart by Andromeda's gravity. The streams are faint, requiring deep surveys and careful analysis to detect, but they're everywhere, wrapping around the galaxy in complex patterns. Some streams are thin and well-defined, indicating recent disruptions. Others are broad and diffuse, their stars scattered over time. By studying the stream's positions, velocities, and stellar compositions, astronomers can reconstruct the orbits of the disrupted galaxies, figuring out where they came from and when they were destroyed. The streams are also a probe of dark matter. Their shapes are influenced by Andromeda's gravitational field, including the dark matter halo. By modeling the streams, astronomers can map the dark matter distribution, learning about this invisible component that dominates the galaxy's mass. The evidence found by Hubble, the Hubble Space Telescope, has revolutionized our understanding of Andromeda. Its sharp vision has resolved individual stars throughout much of the galaxy, allowing astronomers to measure distances, ages, and compositions with unprecedented precision. Hubble has mapped the stellar halo in exquisite detail, revealing the tidal streams and substructures left by ancient mergers. It's captured stunning images of star-forming regions, showing the intricate structures of gas and dust, where new stars are being born. Hubble has measured the motions of stars near Andromeda's core, providing evidence for the supermassive black hole, and it's studied Andromeda's satellite galaxies, revealing their structures and interactions. Some of Hubble's most iconic images are of Andromeda, vast mosaics containing over 1 billion pixels, showing hundreds of millions of individual stars. These images aren't just beautiful, they're scientific gold mines, data sets that astronomers will be analyzing for decades, extracting information about this nearby galactic giant. The infrared views by Spitzer. While Hubble sees visible light, the Spitzer Space Telescope saw infrared, revealing different aspects of Andromeda. Infrared light penetrates dust, showing stars and structures hidden from optical view. Spitzer mapped Andromeda's dust lanes in detail, revealing the distribution of cool, dark clouds where star formation occurs. It detected warm dust heated by young stars, tracing recent star formation across the galaxy. Spitzer also revealed older, cooler stars that emit most of their light in infrared, stars that are faint or invisible in optical light, but contribute significantly to Andromeda's total mass. The infrared views showed that Andromeda's ring structure is more complex than visible light suggests, with multiple rings of different ages and compositions. Spitzer's observations complemented Hubble's, providing a more complete picture of Andromeda's structure and evolution. Together, these space telescopes have transformed our understanding of our nearest galactic neighbor, revealing details impossible to see from ground-based telescopes. The X-ray glow from hot gas. Andromeda glows in X-rays, though faintly. X-ray telescopes, like Chandra and XMM Newton, have mapped this high-energy emission, revealing hot gas near the core, heated to millions of degrees by the central black hole and by supernova explosions. They've also detected X-ray binaries, systems where a normal star orbits a compact object, a neutron star or black hole, and material from the star is pulled onto the compact object, heating up and emitting X-rays. Andromeda contains hundreds of these X-ray sources, each one marking an exotic stellar system. The X-ray observations also reveal supernova remnants, expanding shells of gas from stellar explosions, still hot enough to glow in X-rays years or centuries after the initial blast, and they show the hot halo, diffuse X-ray emission, extending beyond the visible disk, gas heated by stellar activity and gravitational interactions. The X-ray view of Andromeda reveals its most energetic phenomena, processes invisible at other wavelengths. The radio emissions from its core. Andromeda emits radio waves, primarily from its core. Radio telescopes have detected synchrotron radiation, emitted by electrons spiraling in magnetic fields near the central black hole. This radiation suggests the black hole is still somewhat active, though not as dramatically as in a quasar. Radio observations also reveal supernova remnants, which emit radio waves as their shock waves plow through the interstellar medium, and they detect pulsars, rapidly spinning neutron stars, that emit beams of radio waves, like cosmic lighthouses. Andromeda's radio emission is weak compared to active galaxies, but it's still informative. It tells us about the magnetic fields threading through the galaxy, about the activity level of the central black hole, about the population of exotic stellar remnants. Radio astronomy adds another dimension to our understanding of Andromeda, revealing phenomena invisible at optical and infrared wavelengths, completing the multi-wavelength portrait of this nearby galaxy. The role of the James Webb Space Telescope. The James Webb Space Telescope, launched in 2021, is now turning its powerful infrared eyes toward Andromeda. Webb's unprecedented sensitivity and resolution are revealing details never seen before. It's imaging star-forming regions with incredible clarity, resolving individual star clusters, and mapping the distribution of dust and gas with precision. Webb's infrared vision penetrates the densest dust clouds, revealing protostars still embedded in their birth cocoons. It's studying the oldest stars in Andromeda's halo, measuring their compositions with exquisite precision, providing new insights into the early universe. And Webb is observing Andromeda's satellite galaxies, looking for the faintest, most distant companions, testing theories of galaxy formation. Webb's observations of Andromeda are just beginning, but they're already transforming our understanding. Every observation reveals new details, new structures, new questions. Andromeda, even after centuries of study, still has secrets to reveal, and Webb is the perfect instrument to uncover them. The mapping of its spiral structure. Andromeda's spiral structure is complex. Not a simple two-armed pattern, but a multi-armed, asymmetric design. Astronomers have spent decades mapping this structure, tracing the spiral arms through their dust lanes, their star-forming regions, their concentrations of young stars. The arms aren't fixed features, they're density waves, patterns that rotate through the disk at a different speed than the stars themselves. As gas and stars pass through these waves, the gas compresses, triggering star formation, lighting up the arms. Behind the wave, the bright young stars age and fade, and the arm dims. This creates the illusion of solid arms, but really the arms are temporary patterns, constantly refreshed by new star formation. Andromeda's spiral structure is shaped by its rotation, by the gravitational influence of its satellites, and by past mergers that disturbed the disk. Mapping this structure helps astronomers understand how spiral galaxies work, how density waves form and persist over billions of years. The measurements of its rotation curve. By measuring the velocities of stars and gas at different distances from Andromeda's center, astronomers construct a rotation curve, a graph showing how orbital speed changes with distance. In a simple system, where all the mass is concentrated at the center, orbital speeds would decrease with distance, just like planets in the solar system. But Andromeda's rotation curve is flat. Stars far from the core orbit just as fast as stars closer in. This flat rotation curve is evidence for dark matter. The visible matter, stars and gas, isn't enough to explain the orbital speeds. There must be additional, invisible mass extending far beyond the visible disk. This dark matter halo contains most of Andromeda's total mass, providing the gravitational pull that keeps the outer stars bound to the galaxy. Andromeda's rotation curve is one of the clearest pieces of evidence for dark matter's existence, a mystery that remains unsolved despite decades of research. The discovery of its double nucleus. In the 1990s, Hubble made a surprising discovery. Andromeda's core appeared to have two bright peaks, separated by just a few light years. This double nucleus was puzzling. Was it two black holes, not yet merged from a past galaxy collision? For years, that was the leading theory, but further observations complicated the picture. The two peaks have different characteristics. One is brighter and more concentrated, the other more diffuse, and they're not stationary relative to each other, which you'd expect if they were two separate black holes. The current interpretation is that the double nucleus is an illusion. The true center, where the supermassive black hole sits, is the dimmer of the two peaks. The brighter peak is actually a disk of stars orbiting the black hole, seen from an angle that makes it appear offset from the center. It's a geometric effect, not two separate structures, but the discovery sparked years of debate and research, showing that even nearby, well-studied galaxies can still surprise us. The mystery of its central region. Andromeda's core remains mysterious, despite intensive study. The double nucleus, the off-center features, the asymmetric distribution of stars, all point to a complex history. The leading theory is that Andromeda underwent a major merger relatively recently, within the last few billion years. This collision would have disrupted the core, creating the structures we see today. The merger might also explain Andromeda's large stellar halo, its numerous tidal streams, and its high star formation rate compared to similar galaxies. But the details remain unclear. Which galaxy did Andromeda merge with? When exactly did it happen? How did the merger reshape the core? These questions are still being investigated. The central region of Andromeda is a puzzle, a complex knot of stellar orbits and past interactions that astronomers are slowly untangling. Every new observation adds a piece, but the full picture remains elusive. The clues about its past mergers. Andromeda's structure is full of clues about its violent past. The warped disk, bent out of the galactic plane, suggests a past interaction with a satellite galaxy. The off-center features in the core point to a major merger. The stellar streams wrapping around the galaxy are direct evidence of consumed satellites. The high-velocity dispersion of stars in the halo, their random motions rather than ordered orbits, indicates they came from multiple sources. Even the chemical composition of stars varies in ways that suggest different origins. By piecing together these clues, astronomers reconstruct Andromeda's history, identifying at least two major mergers in the past few billion years, plus dozens of minor ones. Each merger added mass, triggered star formation, and left scars in the galaxy's structure. Andromeda's past was violent, chaotic, a series of collisions that built it into the giant we see today. And its future holds at least one more major merger, when it collides with the Milky Way, the signs of starbursts long ago. Andromeda's star formation history hasn't been smooth. There have been periods of intense activity, starbursts triggered by gas inflows or galaxy mergers. Evidence for these starbursts comes from stellar populations, groups of stars with similar ages, formed in brief bursts, scattered throughout the galaxy. These populations stand out against the background of steadier star formation, indicating specific events when star formation spiked. The most recent major starburst may have occurred a few billion years ago, possibly triggered by the same merger that created the disturbances in Andromeda's core. Older starbursts are harder to identify, their evidence scattered and diluted by billions of years of stellar evolution. But they're there, written in the ages and compositions of stars, markers of past epochs when Andromeda blazed with the light of newborn suns. These starbursts are a reminder that galaxies evolve in fits and starts, with quiet periods punctuated by violent bursts of activity. The motions of its star clusters, Andromeda's globular clusters, are in constant motion, orbiting the galaxy in wide elliptical paths. By measuring their velocities, astronomers probe Andromeda's gravitational field, mapping the distribution of mass, both visible and dark. The cluster's motions reveal that Andromeda's dark matter halo extends far beyond the visible disk, perhaps hundreds of thousands of light years from the center. Some clusters have unusual orbits, moving in directions different from the bulk of the cluster population. These oddball clusters might have been captured from satellite galaxies during mergers, their orbits preserving evidence of their origin. Others move in streams, groups of clusters following similar paths, suggesting they form together or share a common history. The motions of star clusters are a powerful tool for understanding galaxies, providing information about mass distribution, merger history, and gravitational dynamics that's hard to obtain any other way. Andromeda's clusters are like test particles, probes, mapping the invisible forces that shape the galaxy. The edge where its disk fades to darkness. Andromeda's disk doesn't have a sharp edge. It fades gradually, the density of stars decreasing with distance from the center, until eventually it's indistinguishable from the background. This fading edge is fascinating. It's where the galaxy transitions from a structured disk to a diffuse halo, where star formation has ceased, where only the oldest stars remain. The exact location of the edge depends on how you define it, what threshold of stellar density you choose. But somewhere around 100,000 to 120,000 light years from the center, the disk effectively ends. Beyond that, individual stars become sparse, scattered through the halo, no longer part of the organized structure. The edge is a frontier, the boundary between Andromeda's organized interior and the near emptiness beyond. It's not a wall or a barrier, just a gradual fading, a transition so smooth you'd barely notice if you were traveling through it. But it marks the limit of the galaxy as a coherent structure, the faint halo beyond the visible. Beyond Andromeda's bright disk lies the halo, a vast sphere of old stars, globular clusters, and dark matter. The halo is faint, contributing only a small fraction of the galaxy's total light, but it contains a significant amount of mass. The stars in the halo are ancient, formed early in Andromeda's history, or captured from disrupted satellite galaxies. They orbit in random directions, their motion dominated by the galaxy's total gravitational field rather than the organized rotation of the disk. The halo extends far beyond the visible edge, perhaps as far as 1,000,000 light-years from the center, overlapping with the Milky Way's halo. Mapping the halo is difficult because the stars are so spread out, so faint, but it's important. The halo preserves evidence of Andromeda's formation and growth, a fossil record of ancient mergers, and it's where most of the dark matter resides, the invisible mass that dominates the galaxy's gravitational field. The streams that connect to the Milky Way. There's growing evidence that Andromeda and the Milky Way are already connected, not just gravitationally, but physically. Faint streams of gas, and possibly stars, may stretch between the two galaxies, bridges across the intergalactic void. These streams would be incredibly diffuse, barely detectable, even with sensitive instruments, but their existence would show that the two galaxies have been interacting for a long time, possibly exchanging material. Some dwarf galaxies in the local group show signs of past interactions with both Andromeda and the Milky Way, suggesting they've traveled between the two giants, perhaps carrying material with them. These connections are tenuous, fragile, but they hint at a complex web of interactions linking all the galaxies in the local group. Andromeda and the Milky Way aren't isolated islands. They're part of an ecosystem, influencing each other even before their eventual collision. The evidence of past interactions. Andromeda and the Milky Way have likely had close encounters in the past, long before their final merger. Computer simulations suggest that the two galaxies may have passed within a few 100,000 light-years of each other, several billion years ago, close enough for gravitational interactions to affect both. Evidence for such encounters is subtle, but potentially present in the disturbed structures of both galaxies, in the motions of satellite galaxies, in the streams of gas that may connect them. These past interactions would have been brief, the galaxies swinging past each other and then separating, not yet ready for the final merger. But even brief encounters can have lasting effects, triggering star formation, disturbing disks, altering orbits. Andromeda and the Milky Way have been dancing around each other for billions of years, their mutual gravity pulling them together in a slow, inevitable spiral. The dance is almost over. The final embrace approaches. The shared future of two galaxies. Andromeda and the Milky Way share a future. They're bound together by gravity, approaching each other at 110 kilometers per second, destined to merge in about 4 billion years. This shared destiny links them in a way that's profound. They're not just neighbors, they're partners in a cosmic dance that will end in union. Everything we learn about Andromeda teaches us about the Milky Way's future. The merger will affect both galaxies equally, transforming both into something new. Milky will be the child of two galaxies, carrying forward the legacy of both. In a way, studying Andromeda is studying our own future, looking at the galaxy that will one day merge with ours, trying to predict what will happen when these two giants collide. The shared future creates a connection, a bond between Andromeda and the Milky Way that goes beyond mere proximity. They're partners in destiny, two galaxies whose stories will ultimately become one. The fate of the solar system in the collision. What will happen to our solar system when Andromeda and the Milky Way collide? The most likely answer: not much. The solar system will probably survive intact. The Sun, if it still exists, and it should, it has about 5 billion years left, will find itself in a new orbit within Milky. But the planets will still orbit the Sun as they always have. Direct collisions between stars are incredibly unlikely. Space is mostly empty, and even in a galactic collision, stars are so far apart that they'll pass right by each other. The solar system might be flung to a different part of the galaxy, perhaps far from the core, perhaps closer. The night sky will change dramatically, but the Sun and planets will endure. There's a small chance, very small, that gravitational interactions could eject the solar system entirely, sending it wandering through intergalactic space. But that's unlikely. Most likely, the solar system will simply find itself part of a new galaxy, Milky, orbiting in a different configuration, but otherwise unchanged. The beauty that will fill our sky, if humans or their descendants still exist in 4 billion years, they'll witness one of the most beautiful sights imaginable. Andromeda, growing larger in the sky over millions of years, eventually stretching across the entire heavens. The two galaxies interpenetrating, their spiral arms tangling, creating complex patterns of light, regions of intense star formation, glowing brilliant blue and pink, visible across the sky. The night will be filled with light, more stars visible than at any time in Earth's history. Multiple galactic cores moving around each other before finally merging. It will be spectacular, terrifying in its scale, beautiful beyond words. The collision will take place over hundreds of millions of years, so no single generation will see the entire event. But those alive during the peak of the merger will see a sky transformed, a cosmic light show playing out overhead. If anyone is there to see it, it will be the greatest show in the universe. The last sunrise before the merge. There won't be a single moment when the merger begins or ends. It's a gradual process, playing out over billions of years. But somewhere in that long span, there will be a last sunrise before the final union. A last morning, when Andromeda and the Milky Way are still recognizably separate. Maybe it will be when the two galactic cores finally merge, creating a single, unified center. Or maybe it will be when the spiral structures are finally destroyed, replaced by the smooth glow of an elliptical galaxy. Whenever that moment is, it will mark the end of an era. Two galaxies that have existed separately for over 10 billion years will cease to be. Their individual histories will end, and a new history, the history of Milkomeda, will begin. It's an ending and a beginning, a transformation as profound as any in the cosmos. The last sunrise of two galaxies, the first dawn of one, the stars that will wander the void. Not every star will remain bound to Milkomeda. During the merger, gravitational interactions will fling some stars into intergalactic space, ejecting them from the galaxy entirely. These stars will wander the void, orphaned, drifting through the darkness between galaxies. They'll still shine, still burn their fuel, but they'll be alone, separated from the galaxy that birthed them. If any of these stars have planets, those worlds will see a strange sky, no galactic disk overhead, no spiral arms, just a few scattered nearby stars, and in the distance, the glow of galaxies far away. These wandering stars are a sad consequence of the merger, casualties of the gravitational chaos, but they're also beautiful, in a melancholy way. Lone lights in the darkness, travelers with no destination, burning quietly in the void. Most stars will remain in Milkomeda, but a fraction will be cast out, wandering the universe alone. The calm end of the cosmic dance. Eventually, the dance ends. After billions of years of orbiting, approaching, colliding, and merging, Andromeda and the Milky Way will finally settle into their final form. Milkomeda will be stable, its stars in equilibrium, its structure settled. The violence of the merger will be a memory, preserved only in the galaxy structure, in the streams and shells that mark past collisions, and a calm will descend. Milkomeda will orbit through space, slowly rotating, its stars aging, its gas depleting, moving toward a quiet old age. The cosmic dance, which began billions of years ago, when these two galaxies first felt each other's gravity, will be over. The dancers will become one, moving forward together, no longer separate, but unified. It's a peaceful ending to a violent process, a reminder that even chaos, given enough time, settles into order. The dance ends, the calm begins, and Milkomeda continues, forever changed. The legacy of Andromeda's light. Andromeda's light has been traveling to us for over 2 million years, and it will continue to reach us until the merger. That light carries a legacy, a story of a grand spiral galaxy, a cosmic neighbor, a future partner. Andromeda has taught us that we're not alone in the universe, that galaxies are countless, that the cosmos is vaster than we ever imagined. It was the key that unlocked modern cosmology, the evidence that proved the universe extends far beyond our own galaxy, and it remains important, a laboratory where we study star formation, galactic structure, dark matter, and the processes that shape galaxies. Andromeda's light is more than photons. It's information, history, inspiration. Every astronomer who points a telescope at that faint, fuzzy patch in the autumn sky is continuing a tradition thousands of years old, adding to our collective understanding of the universe. Andromeda's light is a gift, and its legacy will endure. The lessons it taught about our universe. Andromeda has taught us so much that the universe is filled with galaxies. Not just one, that galaxies have structure, spiral arms and cores and halos, that they contain dark matter, invisible mass that dominates their gravity, that they evolve over time, growing through mergers, forming stars, aging, that they're connected, part of groups and clusters bound by gravity, that they're dynamic, not static paintings, but living systems that change over billions of years, and that they have futures, destinies written in their motions and interactions. Every lesson learned from Andromeda applies to galaxies throughout the universe. It's a template, a nearby example of processes that happen everywhere. By studying Andromeda, we understand not just this one galaxy, but galaxies in general. It's a Rosetta Stone for galactic astronomy, translating the distant and abstract into something we can observe, measure, and comprehend. The proof that galaxies are many. Before Andromeda's true nature was revealed, we thought the Milky Way was the universe. Everything we could see, we assumed, was part of our one galaxy. Andromeda shattered that assumption when Edwin Hubble measured its distance and proved it was far beyond the Milky Way's boundaries. He proved that galaxies are many, not one. The universe expanded overnight in human understanding. Suddenly, there were thousands, millions, billions of galaxies, each one a collection of stars, a cosmos unto itself. That revelation changed everything. It changed how we see ourselves, how we understand our place in the universe. We went from thinking we were central to realizing we're one small part of an incomprehensibly vast cosmos. Andromeda was the proof, the evidence that forced us to expand our perspective. And that proof came from a faint smudge of light, barely visible to the naked eye, but containing worlds beyond imagination. The symbol of connection across space, Andromeda is more than a galaxy. It's a symbol of connection across vast distances, of neighbors separated by unimaginable gulfs, yet bound together by gravity, a symbol of the future, of the merger that will one day unite it with the Milky Way, a symbol of exploration, of humanity's drive to understand the cosmos, to look beyond our world and wonder what's out there. When you see Andromeda in the night sky, you're seeing light that traveled for millions of years to reach you. You're connected, in that moment, to something ancient and distant. That connection is profound. It reminds us that we're part of something larger, that the universe is full of wonders, that there are always more mysteries to explore. Andromeda is a symbol of our curiosity, our wonder, our place in the cosmos, a neighbor we can see but never visit, a connection across the void. The eternal journey of starlight, starlight from Andromeda, has been journeying through space for over 2 million years. It left when our ancestors were just beginning their evolutionary journey, when the future of humanity was uncertain, when Earth was a very different place, and it traveled, uninterrupted, across the intergalactic void, through the darkness, carrying information about a distant galaxy. That journey is eternal, in a way. Light is always traveling, always moving, from every star to every point in the universe. Andromeda's light fills the cosmos, spreading outward in all directions, reaching worlds we'll never see, carrying the story of its galaxy to distant corners of the universe. And our light does the same, the combined glow of the Milky Way spreading outward, perhaps reaching civilizations around Andromeda's stars, if any exist. Starlight is a messenger, eternal and tireless, connecting everything in the universe through the simple act of shining, the universe still expanding around them. While Andromeda and the Milky Way are approaching each other, bound by gravity, the universe around them is expanding. Distant galaxies are receding, carried away by the expansion of space itself, moving faster the farther away they are. Eventually, in the far future, after Milky has formed and settled, after trillions of years have passed, the universe's expansion will have carried away all but the closest galaxies. Milky will be alone, isolated in a vast, dark void, the only galaxy visible in its sky. The cosmic horizon will have shrunk. The universe will appear smaller, emptier, lonelier, but that's inconceivably far in the future. For now, Andromeda and the Milky Way are approaching, moving against the cosmic expansion, drawn together by gravity. They're swimming upstream, defying the universe's general tendency to spread things apart. And for a few billion more years, they'll continue that approach, until finally they merge, creating something new in an ever-expanding cosmos.